Professor Dieter Hoffmann from the Technical University in Darmstadt, Germany, and his talk today is about high energy density physics with intense ion and laser beams.
Okay. So I thank my co-organizers to letting me speak here and chairing this wonderful meeting. And I changed my title a little bit from high energy density plasma physics to high energy density science, because we had a workshop just last week and we thought high energy density science meets the topic much better than plasma physics, because in Germany plasma physics is related to tokamak physics, ITER, and gas discharges. So this talk is a follow-up of Stefan Neff's talk yesterday. However, from a slightly different perspective, and not from the management perspective. So I see as a user things slightly differently, at least sometimes. So this was from July 11 to 14, the collaboration meeting. And these are the people, and some of them, if you look very sharp, are here again. And the reason why we met was that FAIR is now in a stage where all the experiments that are going on there have to readjust and to refocus and to think about the first day experiments and things like that. And we thought that this is also the time to inaugurate a new collaboration, and the name is not yet fixed, but it probably goes into the direction of high energy density science at FAIR. So what FAIR is was introduced yesterday already by Stefan Neff, but let me show it again. This is what we dream that FAIR should look like in the future. So to the left of this picture, you see GSI. This is the National Accelerator Laboratory for Heavy Ions at the moment. And to the right side of the red boundary is the new facility FAIR. At the moment, these are two independent companies. GSI is a national laboratory in Germany, and FAIR is an international enterprise by 8 nations, and the main contributor from outside is Russia. So this is what the accelerator plan looks like. You see here in green, this is the existing facility of GSI, and this accelerator should later inject into what we call FAIR. FAIR is for Facility for Anti-Proton and Ion Research. It's not a very clever name, but what can you do when your boss says, I have a good idea, what do you think about calling it FAIR? So we all said yes, however, so it's now FAIR. What you see here are actually two synchrotrons, SIS 100 and 300. This is the different magnetic rigidity, and this is the plan, as it says, for the full version. In a project like this, which comes to 1 billion, actually when we in 1990 or so wrote the proposal, we had 650 pages and asked for 650 million euro. So 1 million per page. And so the price has gone up, so the efficiency of writing is better, so it's probably now 2 million per page, and it is going up to 3. That's due to budget restrictions, we had to go from the full version to what we call now the modified start version. And in the modified start version, these rings down here essentially are skipped, so this needs a new planning. This is how GSI and FAIR look today. So this is the existing national laboratory, and here you see there will be the FAIR accelerators, and this circular area here is where the synchrotrons should be. So we started, or I started to think about it at least in 1998. So there was planning and all this, and then finally the first was cut down. And here are pictures from 2013 and 2014. This looks quite busy. I was talking about budget problems, and here you see people were drilling. Unfortunately, there was no oil. So, no, the reason for this was the first stumbling block that we encountered. The ground was determined to be not stable enough. So 1,200 concrete pillars, 60 meter deep, 2 meters in circumference, were rammed into the ground, and it is now stable. And this was from 2013 to 2014. And down here, now I take a picture every week, you see nothing moving. Why is this so? And one of the reasons is that civil construction did not start. This is just a scheme, but you can imagine that this is already a nightmare. So, there were also legal problems because people who have to pay say this is one building, the planners say these are 14 buildings, and so they had legal fights about this because this is about their salary. But anyway, you can see that it is really a difficult task to do this. Now let's come a little bit to the physics. In the 1990s, when I joined this, we had a director who said, well, what are you dreaming of? What do you want to do in your field with your facility? I don't speak about the nuclear physics, I just address high energy density science. Well, and at that time, look at this. This is a calculation by Meyer Terween about the target behavior of an indirectly driven target driven by intense heavy ion beams. So at already now, or still now, we think that we need a whole round temperature of approximately 300 electron volt. And it was, of course, clear that in our wildest dreams, the new facility would not be capable to ignite a pellet. So we wanted to do basic research on matter under these conditions. And you see I have the fields here, warm, dense matter, strong hydrodynamics. And the idea at that time was to heat a microscopic sample of matter into what we call the radiation regime. That means you put energy into your sample, and most of this energy that you put in is given off as radiation. While further down you have warm dense matter, you have hydrodynamics. Well, this was what we dreamed of, and then first people started to worry about the budget. And one of the first ideas that came up was to shrink the magnet size in diameter, which reduces cost, but it reduces also intensity. Well, you can think of the limit. If you go to zero, you have no cost, but also no intensity, and this does not make sense. So, Stefan yesterday showed you this part of the table, and what you see here, we will come up with 1 to, let's say, 60 kilojoule per gram deposited into matter. So this will be in this regime, here, in this regime, and you see you come into the regime of warm dense matter, 1 to 10 electron volts, with high Z material a little bit more. And at the moment we are doing at GSI experiments at 1 kilojoule per gram, and there will be an upgrade that will take us to 3 kilojoule per gram. So this stream we had to give up. So the next step that you do is you look at the parameters, and This is one of the, we saw slides like this more often during this conference. So this is the density. So here you have solid state density. This is the temperature, 1 electron volt, 10 electron volts, and it is about this area that you can address. However, we still talk about fusion, and our argument is if you want to go up here where inertial fusion is, your matter goes through the phase of warm dense matter, and depending on the properties there, it may determine the outcome depending on how much energy you put into this. So we were discussing along these lines on the workshop, and well, the main pillars of the research that we suggested will still be valid also when FAIR is starting in a couple of years. And the first class of experiment we call high hex. This is heavy ion heating and expansion. So you see here a target that is target foil that is irradiated by an elliptical beam, so it's fully irradiated, and so the sample should be heated more or less homogeneously if the beam is like this. So you have uniform isochoric heating if you do it fast. So while you put energy in, your sample does not move very much, and at the end of energy input, the sample starts to expand, and you achieve numerous high entropy, high energy density states. And this is one of the landscapes that we plotted already in 2002. This is Folate. So usually with lasers and high explosive, you go along the principal Hugonot, and you will find a lot of experimental data here. What we will do is isochoric heating, and we come up along this line, and then we do the isentropic expansion. And if we are in this neighborhood here, we can address the area of critical points of many materials. And yesterday there was the example of uranium, and as I told you, we did one uranium experiment, but then GSI was afraid of this. So if you do experiments like this, what can you measure and how do you measure? This is an example of the setup we are using at GSI. Here again, you have a foil that is heated. These are sapphire windows, and after a while this will start to move. So what you can measure is by backlighting, you can measure the expansion velocity. When this thing hits the sapphire window, you will induce a shock wave, and from this you can recalculate the pressure in your sample. But this thing is also hot, it radiates, you can measure the radiation. And an example for this is shown here. This is a tungsten foil that is heated, and you see it's quite hot here. But actually we do not investigate this area, but we investigate this area where we have more homogeneous heating. And then we have a spectrometer. This is a pyrometer that looks at different wavelengths with high time resolution. And you see in this case of tungsten, we reached approximately 1 electron volt by heating, and then we let this thing expand. So we did this experiment for a large number of ions. From here you see there is also the uranium dioxide, and this places your critical points much better on the list. So this is what you do for high hex. Now the other experimental scheme is isentropic compression. How do you compress with the beam? Now we know how you expand it. If you want to compress, you have to make a more clever target, and this could be a hollow lead cylinder filled with your sample. Let's think of cryogenic hydrogen, and then you have to heat the outer cylinder without heating the interior, and then this will expand and press on the inside, so the inside will be rather cold, but cold compressed, and the calculations, and some of the calculations were shown by Stefan today. We think that we can reach 5 megabar or a little bit more. In order to have this circular beam, we have to ask people who are still used to having TV screens, tubes, where the electron beam was wobbled around to make the picture. Today this is different, so the young people will not remember this anymore, but this scheme is used to make this circular beam. Now there is a problem. If this goes on, how do you diagnose the inside? So you have a high Z temper and want to see density differences in the inside. Well, of course, you must make use of penetrating radiation. You can use X-rays and a lot of things, but assume you have X-rays. Once they are energetic enough to penetrate the lead, the contrast on the hydrogen is not very good anymore. And so the idea was to go to proton radiography. So charged particles make energy loss, nuclear collisions, Coulomb scattering. Coulomb scattering will mainly blur your picture, but the other things you can use for imaging. This is of course not our idea, but this was successfully invented and tested in Los Alamos, and exactly this makes problems at GSI, because as soon as we started to talk about proton radiography, they said this is defense-related research, you must not do this. So what we do is we call this not radiography, but we call this microscopy, and this is then okay because it gives you immediately the idea that it is not such kind of samples that you want to analyze, but these kind of samples. However, people in our automotive industry like BMW and others would be very interested to have a BMW motor radiographed and while it is running. So for this case, microscopy is not the thing, the way to go, but maybe we find out about things. So now you have to look a little bit more closer. The idea is to do something with the ion beam on the target, and then you need a diagnostic beam from the other side. And so the idea is here having a proton linac. This will accelerate to 4.5 GeV, then go along here and here and here into our cave, and the main ion beam comes from this side. So this would be a new diagnostic. And when management told me, at that time I was also the collaboration speaker, that we have to save money, I told them, look, intensity is quite nice, and the more the better, but it is not everything. If you want to be at the forefront of science, you must have the best diagnostic that you can get. And therefore, we want for diagnostic purposes this proton microscopy, and we want to have a powerful laser also for diagnostic. For the laser I will talk later. However, this beamline here is dropped. It will cost 20 to 30 million, and if we have the money later, we will install it. So we have to have other ideas, but let me go on. So we call this prior proton microscopy for FAIR, And our idea to test this was to do it with permanent magnetic quadrupoles. This was then a project of only 180,000 euro with a graduate student and a couple of other students. This thing is installed at the beamline at GSI, and this is the outline. And here you have a picture, and at the very end you have a scintillator that looks at the picture, and you record this. Our collaborators in Moscow at ITEP, they were the expert in getting the magnets in shape and putting it together into a quadrupole system that you can see here. So it has a 1.8 Tesla pole tip that is quite good, and of course we had to make sure about linearity and all this. And when we had everything set up, we did an experiment, and I like the example with the watch for the simple reason in high energy physics people take a watch, slam it on the floor and pick up the pieces and try to find out how a watch works. And so we do it a little bit the other way, and you see this gives quite good resolution, and on an exploding wire experiment we came up with spatial resolution like this. So this experiment was more or less successful. However, the permanent magnets deteriorated due to radiation damage. This shows here how the radiation damage was, so before and after. So there was a deterioration of the magnetic field. You can refurbish them, and we are thinking about this, but at the moment there is no need. What we want to do is, for fair, we want to go with electromagnets anyway, because we have a varying energy, and so this can much more easily be adjusted. And from the synchrotron we may get protons up to 10 GeV. The principle that people at Los Alamos designed, you have 4 quadrupoles, and you have in what we call the Fourier plane a focus point according to the scattering angle. So the very large scattering angle can be scraped off, and you have an image with a magnification of let's say 4 or something like this. What you have to pay attention to is object scattering, chromatic aberrations, and detector blur. And you see the momentum is always in the denominator, so higher energy should in principle give you a better resolution. And this is where we are a little bit better than Los Alamos. They work with 800 MeV and we have 4.5 and up to 10 GeV available. Now that the diagnostic beamline was skipped, we have to do something else. We have to produce our high energy density matter by other means. My colleagues in Russia think of a chamber that holds explosives. That you see there, we did explosions up with 40 grams of TNT equivalent. They want to have a little bit bigger chamber with up to 1 kilogram. However, this is not easy to talk GSI and FAIR to redo this again. And therefore, we have the idea of building a light gas gun. I'm coming to the end, and this is the project of one of my graduate students. And actually, this is more or less copied from the BMW methane motor. Well, this is something we still can do in Germany, build automobiles and motors. On others, we lost our edge. And all the parts that you see here are ready, and it will be assembled. And since the time is progressing, so what we think is that we can come up to a flyer plate with velocities of, let's say, 3 kilometers per second. This is not the maximum that has been achieved, But with the new kind of diagnostic, even doing old experiments, we probably have new insights, and we think that we should now go for phase transitions in cerium that we can do. Okay, this was shown by Stefan yesterday, so I can skip this. Just one word, GSI is at the moment the only facility where we have an ion beam and a nice laser beam. So there are interesting experiments I cannot talk about, but our community thinks that we should have a laser with this parameter, and we are fighting at the moment for this. And at the end of our fight, we should have this laser for 40 million ready when FAIR is ready to run. And so I come to the end. Well, this was the workshop last week we had, and we started a new collaboration. And anybody in here who is interested in is invited to join. Thank you.
Questions?
Can you quickly go back to the slide where you're listing the laser parameters? It was about 3 slides back.
It's clear that you.
Yeah, that one.
This?
Yeah, just quick shot.
So it should be a kilojoule machine with a short pulse and a long pulse option for backlighting and other kind of diagnostics.
All right, I was just commenting. 40 million euros sounds like a lot of money for the project.
Well, we have to ask for 40 million, and if we get 10, we will find a solution. No, our laser experts thought, together with people from Livermore, that's what we have to have.
Don't ever believe the guys from Livermore. They're very expensive.
They are, we also have to build a house for this. The project we had before, my idea was 3 million in 3 years. And then the management came in, and it was 20 million in 10 years. So this is how it goes.
Next question.
So about the high effects, you have a wobbler. And what are the parameter for the wobbling frequency and fluid motion time scale also?
This is an interesting question, because if you start with your beam, you have this point. Next time around, it's you hit this twice and 3 times. So the question is, how stable is the target, and how fast do you have to rotate it? I'm an experimentalist. I said, if you're in 100 nanoseconds, if you do it 10 times, it will work. And then 10 theorists went to work for 2 years, and they came out, if the beam shape is properly, so Gaussian, 10 times. So which means you have a rotation in 10 nanoseconds.
I see. So the fluid motion time scale is also 10 nanoseconds more?
Yeah.
Okay, then
So we have a beam pulse of 80 to 100 nanoseconds, maybe 50.
I see.
But in this time it should work. And so the wobbler they are starting to design at ITEP has just these parameters.
And what was the radius of the cylinder?
It's approximately a millimeter. Yeah.
Thank you very much.
Other questions? I have a question.
Thank you very much. Nice talk. So maybe I missed something. So you showed a light gas scan. So what kind of parameter do you want to get by this method?
Okay, I skipped the parameters. Oops. The flyer plate that we want to accelerate should go up to 3 kilometers. Wait a minute. So maximum helium pressure 1.6 kilobar, barrel diameter 12 millimeter, barrel length 2 meter. This is because we do not have more space, and up to 3 kilometers per second, and a flyer plate of 10 millimeters to make a shock wave.
That is for what do you want to measure using this one?
The phase transition, the first experiment will be a phase transition in stereo.
Okay.
Is there another diagnostic that you wish to have that you didn't mention beyond prior? And
well, if we have the laser and if we have prior, then no one else in the world has this combination. And since it will start only 2020 something, I will come up with another idea by that time. All right.
Let's thank Dieter again.